Hello and welcome to Sean White's Solar and Energy Storage Podcast. We are recording from Contra Costa County, California. That's right, Antonio and myself, we live in the same county. And in fact, Antonio lives in the same town where I went to high school. And Antonio Baclig is also the founder and CEO of Inlyte Energy. We recently had him on the podcast at RE Plus in Las Vegas. We were talking in person, and now we kind of have to yell over the hill. So, hey, Antonio, how's it going? What's up over there in Walnut Creek?
Wait, I'm getting some feedback on the microphone. Don't talk so loud.
Okay. I know, it's just a couple of hills in between us. I've actually, rode my bike from here to there before, so.
Great place to live, yeah.
You caught me off guard there. At first, I thought there was some real feedback.
Oh,
so.
Sorry.
No, it's all good. All right. So the last conversation, we were talking about how great your company is with your special battery technology, and all of that's true. And maybe this time we could talk about a few different subjects, such as just kind of basic battery education. I think you would be really good at that because you are very educated and also are good at explaining things. And another thing too is maybe we could talk a little bit about billionaires that think they actually know something about something that they didn't specialize in.
Yeah, I have a lot of thoughts on that. Yeah, on both of these topics. Yeah.
Okay, all right. Which one do you want to start with?
Up to you.
Okay. Well, let's maybe talk about battery technology, because I think billionaires, nobody listens to them anyway.
As it should be.
I'm just kidding. And so some of the things that I was thinking about is just like the basics of like how a battery works, cathode and anode, and separators, and different types of separators. What's up with ions? Maybe even explaining what those things are. And you hear about solid state batteries, what makes them so different. And then there's all these different things that you can use with batteries, like all these different chemicals. And it seems like, I've always thought too, with solar, you're kind of more or less limited to the p-n junction and stuff like that. And then it can only get so efficient. But with batteries, there's so many different types of chemicals. And a lot of times what we're trying to do is make something that's lighter and maybe something that takes up less space. And those are things that people are always working on. And I imagine there's a lot more room for growth with batteries than there is with solar, where you talk about solar efficiency. The sun comes at you at 1,000 watts per square meter, and 50% would be a dream, and it would be 500 watts per square meter, and it would be double of what people are doing today in some of the better solar modules. So you can only do so many doublings there. But I think probably with batteries, there might just be a lot more options, and it takes super smart people like you to figure that kind of stuff out. Other things that I was thinking about is, why is lithium better than lead, and why is sodium the best in the world? That's your technology, of course. Mm-hmm. And then I've seen different tables and things like that, and they list all of these different things that are in batteries, and there are differences in voltages depending on like what the different things are that you put in the batteries. And maybe you could also explain how that works.
Mm-hmm. Yeah.
And then why can't I just take out the lead acid battery in my car and inject some lithium into it and make it work better?
Okay.
And I was just trying to be funny there, of course. Haha. No.
So good. Well, I'm glad we have, this series of podcasts, each 2 hours long, in order to cover all these topics.
Yeah.
So
that's okay to do it. We could do 2 hours, or we could do what some of those podcasters do and do 4 hours,
Yeah.
Or probably better to just do multiple podcasts too. So.
No, I'm happy. It's great to be back. Yeah, thanks for inviting me back on your show, Sean. And yeah, would love to come back again. So let's see how much we can cover today. And
let's do it. Yeah.
I guess maybe I'll give folks an intro in case they didn't listen to the first one about myself, just really briefly about kind of where
Great, for sure.
My knowledge comes from. But, I decided about, I guess it was 14 years ago now, that batteries for grid storage are what I wanted to work on. I was always interested in energy and climate, and was basically watching solar and wind scale every year and come down in cost. And, the problem is they're intermittent. So we need batteries that are super low cost to store energy on the grid for them. So decided that's what I wanted to work on, and then went to Stanford.
And that's kind of forward thinking too, because, you look back 14 years ago and there wasn't that much energy storage on the grid. It was kind of a future thing that people are talking about, like, this is what's going to happen in the future. So I guess you're also a bit forward thinking, what should I invest in?
Absolutely. I intended to be. And, I spent a lot of time thinking about it and actually reading a lot, on my bookshelf. I could talk about the specific books that kind of got me on this path and reports. But, I was approaching it. So I think we should back up even before you get to batteries, because there's a lot of ways to store energy, just period, right? And, there's chemical means, there's electrochemical, there's just strictly electrical. If you talk about capacitors, there's superconducting magnets, there's physical means. So pumped hydro or lifting rocks, there are lots of, I'm probably forgetting one or two here, but, I was looking at, basically, when I decided I wanted to work on storage for the grid, I started out by looking at all of them. And what I was really trying to determine is what's the lowest cost way to do that. And without going through each of them, I'll just say I ended up on batteries, and it seemed to me that batteries were the lowest cost way to store energy. And this was back when lithium ion was, $1,000 a kilowatt hour, not $100 a kilowatt hour like it is now. So, I think that's really proven true. And then within batteries, so then I went to Stanford. I spent 8 years in the material science and engineering department there.
Wow.
Studying with Will Chu. He's an amazing professor. And basically, came in wanting to find the best battery for grid storage. So I really surveyed the battery landscape. I thought a lot about these questions about how do you make the best theoretical battery starting from the periodic table. And I got really excited about what we're doing, the iron and sodium battery, which we talked a lot about in the last podcast. So anyway, that's kind of my background.
Maybe also, just while we're at it, just tell us a little bit about the iron and sodium battery that you're working on, that you're Inlyte Energy, which is the company that you're the founder and CEO of.
Yeah. So founded Inlyte 4 years ago, coming out of Stanford. So the idea is, in a nutshell, I got really excited about sodium metal as the starting point. When you're looking at the periodic table, sodium metal as the best starting point for grid storage. And then I was going down this theoretical path about how do you make the best sodium metal battery. And then I realized that actually it ended up looking like an existing battery technology called the sodium metal chloride battery. So this had been invented in the 80s, and it was invented actually for vehicles and fully commercialized. So there's been about a gigawatt hour of sodium metal chloride batteries deployed in different locations, mostly as telecom backup, as small scale premium UPS systems. So it's been in the battery world, that's pretty niche as a battery technology, but still it's proven itself over decades. And I was looking at this and I said, okay, that actually is the direction I want to go, except that, the commercially proven version of this is too costly. It's expensive. And that's why it's not being deployed more widely when we talk about utility scale, very large applications of storing solar on the grid. And, I said, well, how do we bring that cost down now that the application is grid storage rather than vehicles? And the more I dug into it, the more conviction I built about, there are real straightforward ways to bring that cost down if we reinvent this battery technology, and then we can leverage that 40-year history and bring it to the grid. So yeah, that's kind of the whole idea of Inlyte, is reinventing the sodium metal chloride battery. What we've done is we have taken it from a nickel-based cathode to an iron-based cathode. And we've also redesigned the cells to be much, much larger, much lower cost. But the iron, of course, is way lower cost, more abundant than nickel. Nickel was chosen for vehicles, but iron's better for grid. Yeah, so in a nutshell, that's what we've done.
And you sort of had that for lithium ion batteries too, because you have the nickel in the batteries like the NMC. There's a lot of that battery, but even though they call it a lithium ion battery, a lot of people say lithium. It's more nickel, right?
Exactly.
With the NMC. And then they have the LFP, which a lot of cars have LFP batteries. It's a little bit less energy per weight. And the LFP batteries are almost in all energy storage systems these days that are, lithium ion based. So
Exactly. That's a perfect analogy. And LFP stands for lithium iron phosphate. Of course, iron here, Fe, is when you write the chemical formula. But yeah, it is more abundant materials than the nickel and cobalt based metal oxide cathodes. So, I just also want to, while we're on the topic of Inlyte, and then we can go off it, but, we last spoke at RE Plus a couple months ago in September. It's kind of mid-November right now. And it's, there's a lot of exciting stuff going on for us. We've made our first modules now that we're going to deploy in our first pilots early next year, early in 2026. We're going to deploy that Southern company. So we have them coming out to our site in a couple of weeks to view, witness the modules working, integrated with inverters, BMS, EMS. So yeah, been lots of exciting milestones, and I think we'll be making a lot of waves next year when that goes out.
Great. Awesome. Okay. Well, good. That sounds like a good battery. I want to get a whole bunch of Inlyte Energy batteries from you as soon as I can.
And they're ones we can make in the US, and we can source the materials in the US. So, that's what really excited me nowadays. I just got back on a flight today. I was out looking at a site to manufacture the batteries here in the US. So
good. Okay.
But shall we back up and talk about batteries more generally?
Yeah. Let's talk more about just like batteries and stuff. So maybe, I think probably a good place to start is like anodes and cathodes.
Yes. So, I think people are pretty familiar with, the alkaline batteries that you put into your devices, AA batteries, AAA batteries. They have a negative side and a positive side, and you have to make sure you put it on the right.
You know what I can't figure out though is like, why is a AAA battery smaller than a AA? Because a AA is bigger. And it's got like less A's. You would think that they would put more A's. It's like American wire gauge or something. The higher the number, the smaller the wire.
I don't know that one. We'll have to ask ChatGPT about that one. But, so people are familiar that the batteries have two terminals, right? So the negative side is the side of the anode, and the positive side is the side of the cathode.
I'm always wondering when they're going to come up with tripolar batteries.
Yeah.
Like three-phase DC and crazy stuff like that doesn't exist in this universe.
That's super interesting. You have me thinking about this right now. I don't know if there's a reason. I mean, you could make a system that has 3 electrodes, but why would you make that into a commercial device? I'll have to think about that more, Sean. But
you're going to turn my joke into reality. That's pretty good.
Well, electrochemists make 3 electrode setups all the time to test what's going on in batteries or fuel cells or electrolyzers. But anyway.
But that would be maybe something more like bipolar, something like that?
Yeah, so batteries have 2 sides, right? And I think the thing to understand about batteries is that it's a way of harnessing chemical energy, but harnessing that as electricity. So that's why it's called electrochemical devices, electrochemical energy storage. And so basically, you have 2 reactants here that you could combine, and they're going to release energy when you combine them and you react them, right? And so, in a chemical reaction, I don't know, let's say hydrogen and oxygen, right? So if you combine them, obviously you release a lot of energy and you get water as a result. So you're just releasing all of that energy as heat. And that would be a kind of explosive combination.
Yeah, I guess there's 2 different ways too that you combine hydrogen and oxygen. One would be with a flame and the other with a fuel cell.
Yes, exactly. And so fuel cells are essentially one-way batteries. They're electrochemical devices that go one way. Batteries, you can reverse that reaction. I mean, you also have primary batteries that are also one way, but anyway, the technologies are extremely similar on a fundamental basis. But, in our case, so in our battery, the reactants are sodium and iron chloride. And when you combine those, you get sodium chloride and iron. So that's kind of the discharged products of the battery.
So that would mean the chloride is the ion going back and forth?
It's actually the sodium. So actually, I'll pick a simpler example to kind of illustrate battery science. There's a company making iron air batteries. It's called Form Energy. So their reactants are iron and oxygen. Mm-hmm. And if you just combine them, you get iron oxide. or rust.
Rust.
Yeah. And that just, it releases the chemical energy as heat. But the way a battery works is you have a membrane that prevents the two sides from being combined. So it creates a blockage. You're preventing that chemical reaction from happening directly. But this membrane allows an ion to pass through. But importantly, it does not allow electrons. And then you have an external circuit that allows the electron to go through. So if you have an ion in this reaction that separates off from an electron, then you can have the chemical reaction occur by the ion going through the membrane and the electron going through the external circuit, and they all recombine on the other side, and you have that chemical reaction, except you were able to harness that energy by the electron going through the external circuit and using that energy in the circuit. So I don't know if it was completely clear, but I think the point is that in a battery, you're harnessing the chemical reaction of two things that want to react.
Maybe another good thing too would be to define an ion.
Oh, yeah.
And is it always a positive ion that goes with an electron?
Right. So yeah, you can have either positive ions or negative ions. You can have oxygen ions as the ion, and then that's a O2 minus. But mostly it's positive ions. I think let's stick to that for now.
Okay.
So in a lithium-ion battery, the ion is literally Li+, so lithium. So lithium is the third element on the periodic table. So normally it has 3 protons and 3 electrons, and the charge is balanced in that atom. If you remove an electron, now you have 2 electrons, which is actually it's kind of a stable form for it, and due to the s orbital, so now we get into quantum mechanics. But you remove an electron, now you have Li+, because it has 3 protons, so it has 3 positive charges, but it has 2 electrons, 2 negative charges. 3 minus 2 is 1, and you have positive 1 plus on the lithium ion. And that's your ion, and that's what's crossing the membrane in lithium-ion batteries. Mm-hmm. In our battery, it's a sodium ion. So sodium also sits in the same column in the periodic table. You can remove an electron from it relatively easily. And then you have a sodium 1 plus ion that's going to cross over the membrane.
Okay, great. And then I always thought it was kind of interesting is like whatever way the electrons are flowing, that's the same way that the ions are flowing, like internal going through a separator. So when you're discharging a battery, you're having an electron go outside of the battery from negative to positive, and you're having one of these ions, so lithium, or in your case, sodium, going inside from negative to positive through the separator.
Yep, exactly. Yep.
Great. So when you're doing this, what drives it?
Yes, that is such a deep question, actually. So,
and you could just make up some quantum mechanics thing and we won't know what you're talking about, but we'll just think that you're really, really smart.
Well, it's, if I wanted to sound smart, I would say it's the lowering of the Gibbs free energy, right? But it's basically that this is something that releases energy. When the battery starts to discharge, that's lowering, it's a reaction that wants to take place.
Mm-hmm. So when you're going, like if we had a lithium ion battery, so the electron is coming from the negative, which is the anode. And also, I guess there's some lithium over there at the anode. And then it's going over to the cathode. So that would be releasing energy at that same time. And then when you're charging it, you're having the lithium and the electron go from the cathode to the anode.
Yes, you got that right. So so let's think about the battery is fully charged. So you have all the lithium, the active lithium is on the anode side, and it's in its highest potential state, highest chemical potential state, where there's the most energy that would be released when these two sides react, right? But we have this membrane in place so they can't react, right? And then we hook up an external circuit to allow electrons to go from the one side to the other. And so if we just had that as a short circuit, so it's just a wire, very, very, very low resistance, then this reaction wants to happen, right? The electrons want to cross along with the ions because that releases energy. It's, thermodynamically favored here. And so if you have a short circuit, you have that reaction happen as quickly as it can because it's releasing energy, and you just have a lot of electrons go really quickly, a lot of lithium ions go really quickly. That heats up the battery. That could then cause an issue because you have some flammable substances in the battery that you don't want to get too hot, and then they could catch on fire. So you really don't want short circuits, and you don't want cells shorting in the battery. Instead, what you do is you have basically a load so that the electrons are going through the circuit, but they're driving work as they go through. They're doing something, causing the electric vehicle to drive, and that slows them down so that the reaction is only happening in a very controlled, slower manner. And, that's how we design electrochemical systems. In our batteries, something nice about the iron sodium battery is even if we have a short circuit in a cell, you have this, reaction happen very quickly. The cell heats up. But because of the type of reactants and we don't have anything flammable in the battery, we don't have a fire that results. So we can have that happen, the cells fail, the module continues to operate. And anyway, just kind of throwing that out there.
Great. Okay. And so then I know when we talk about the anode, I always think of anode has got an N in it for negative, nice. And cathode has a T in it for positive, because a T is sort of like a plus. And sometimes with that anode it's typically graphite, which is like carbon, but there's some silicon in there a lot of times to make it work better to a certain degree. And so I guess what's happening is when the battery's charged, there's a bunch of lithium ions sitting there attached to that graphite. And then when you're discharging it, it's going over to the other side. And when we're talking about LFP, lithium iron phosphate, F for ferrous, then on the cathode there, it is going to be, I guess, iron, but also some phosphorus. It's just like a combination of iron and phosphorus.
Yeah, it's iron and phosphate, so PO4. And so the crystal lattice has iron in it. It has phosphate ions, PO4 2-, and it has Li+ ions. And what you have is when the lithium gets there, the iron, takes that electron. So the lithium stays as an ion, and the iron likes that electron, and it goes from 3+ to 2+ in the lattice.
So say that again. So the lithium combines with the iron? Is that what's happening?
Yeah, it's actually called intercalation batteries. So, this is, and I apologize to the listeners, we're going to get into some material science, but I think it's very interesting.
Let's just everybody use that word today, intercalation.
Yeah.
Nobody will know what you're talking about and they'll be impressed.
Yeah, it's really cool. And it's really kind of the foundation of what started the whole lithium ion battery technology on its course, is figuring out that we can make intercalation anodes and cathodes. So, what we want to do in the batteries, we want to cycle it many, many times. So we want the lithium ion to go from one side to the other, and then back, and then, back and back, all reversibly. And the beauty of intercalation cathodes like this is that the material has a crystal lattice, and the lithium ion basically inserts into that lattice without changing the structure of it. So,
but it remains a lithium ion. It doesn't become like a different molecule.
Yeah, you don't actually form a covalent bonds between the lithium ion and the structure. It's ionic bonds. You could call it ionic bonds.
So is that the way with all batteries? They don't form covalent bonds. They're all ionic?
No, it's not. So, there's other batteries. So, okay, let's see. What's another one we could pick? I mean, the sodium sulfur battery is something that's a very historical battery, but it's not. It's actually the one that has to be like 300 degrees. Yeah, that one.
It works.
And it's anyway a lot more to say. It's related to our technology, but there's reasons I didn't choose to go into that. But in that case, you have sodium combined with sulfur, and it forms new molecules. So you have polysulfides that bond together. So the polysulfides are different molecules.
We interrupt you for a very important announcement. Sean White's Solar and Energy Storage Podcast has been brought to you by Sean White's Solar and Energy Storage Podcast. That's right, Sean White is sponsoring his own podcast, and he wants to remind you to go check out some of his classes. You can go to SolarSEAN, that's solar, SEAN.com, and then click on the links to check out his classes. You can check out his heat spring classes, and you can also hire him to teach classes for you, like at your company, something like that. Now back to the show.
So lead acid batteries do some covalent bonding then.
Right. Well, yeah, you have plating of lead. And so you have actually, that's one reason they can degrade is you can have, you're plating lead and you're taking it out, and that's not as reversible as an intercalation. Intercalation reactions are very reversible. But on the other hand, one limitation is that in an intercalation reaction, you have to have that lattice. So you're kind of limited by the size and weight of that lattice. And one new frontier in lithium-ion batteries is going to conversion electrodes. So you could get higher energy density if you actually just had the things react with lithium. And if you could figure out how to do that in a very reversible manner, then you could kind of use all of the atoms on the cathode as your reactant rather than having this lattice to have to host it.
And then I guess a lattice is like a crystal, right? It's sort of like a carbon makes a diamond. That would be an example of a lattice structure.
Yeah.
And even, I guess, perhaps, would ice be lattice also?
Yeah. Yeah.
So when water gets cold enough, it goes all lattice on you.
Yeah.
All right. And so then inside of the battery, there is, besides the anode, anode and cathode. Put them together, you got an anode. There's the anode and the cathode. And then in between, there is some sort of separator, and it'll let the ions through pretty much. And I know that there's talk of solid state batteries being better. So what's the difference between a solid state battery and a non-solid state battery, and what kind of batteries are you working with? Are they solid state?
That is an awesome question. So to explain the different, and people use the nomenclature in different ways. For me, I like to be more exact when I speak. And so I would reserve calling something solid state when all of the components in it are solids. And
do some people kind of exaggerate like at marketing words, and they go, this is solid state, and it's not really solid state. And you go like, that guy's a liar.
Yeah. Yeah. I mean, so that's what's happened. And, it's fine because it is very different than the normal lithium-ion batteries. So it's fine to draw a distinction. But in the solid state batteries that are currently being worked on and that are closest to being commercialized, so the main thing is you have a solid membrane now. The membrane between the two sides is a solid that's impenetrable, right? So in the lithium-ion batteries, you have the membrane is a porous polymer that basically you have a liquid that's all kind of within the battery. It's called the electrolyte. It goes from both sides. And this porous polymer, keeps the two sides physically apart so they can't actually touch. But you have this liquid that goes through the pores, can get to both sides. And you have lithium ions that are floating around in that liquid and can move through the pores from one side to the other.
So the lithium ions and the electrolyte can go back and forth?
Exactly.
Okay, and what can't go back and forth?
So solid phases that are, the cathode and anode, those are, when they're made, there's binders, like they're kind of glued together, and they're not going to go back and forth. But you could have, so kind of two things happen from this kind of architecture that's not the most ideal in a battery. So one, well, maybe a couple of things. So that electrolyte, is seeing both sides of the battery. And so it has to be stable to the electrochemical potentials on both sides of the battery, which is actually very difficult to find electrolytes that are stable under all conditions. So you have that electrolyte kind of degrade slowly over time due to that. And then the other thing is you can have crossover of, you can have kind of maybe tiny pieces of the active materials break off, like you can have, molecules that could cross over from one side to the other. So you can have active materials that cross over and then degrade the battery over time. So from a battery scientist perspective, the ideal is something that really is really impenetrable and doesn't allow, anything to cross over from one side to the other, except for exactly the ion you want to cross. So there are certain called ionic conductors that can allow only one type of ion to go through, because those ions again, they're fitting through this crystal lattice within the membrane. The ionic conductor has a crystal lattice. That lattice is like perfectly sized for a lithium ion or a sodium ion. And so the lithium ion goes across and you have no crossover of active materials. And so, that's advantageous from a lifetime perspective. It's also can allow you to get to higher energy densities because then you can use things on either side that you couldn't typically use. So on the anode, you can use just the pure lithium metal rather than having to have it in carbon or graphite. And that's because you don't have that electrolyte crossing over to that would react with that with pure lithium metal. So basically it allows you to use some different things that get higher energy density. But the reason it's usually not a purely solid state battery is that on the cathode, normally what people do is they still use liquid electrolytes on the cathode within the cathode because you still need lithium ions to travel within the cathode, and liquid electrolytes turn out to be a good way to do that. In our case, so this is also kind of what led me to this type of battery. We also use a solid membrane. So, the way people talk about it, I could call our battery a solid state battery, although I wouldn't feel good about it because it's not a truly solid state.
Because you're a scientist and not a marketing person that lies.
Yeah, exactly. So
maybe you need to hire some liar to work for you.
Yeah, maybe.
Yeah, or maybe it could be on the continuum. Like, this one is more solid state than that solid state battery.
Yeah.
Is anybody making anything that you would consider solid state or commercially or not?
So there have been announcements about it. I have not seen anything commercial in terms of kind of the real solid state where you have a ceramic separator rather than a polymer membrane. QuantumScape, of course, comes to mind. They're here in the Bay Area. They've been working on this for a long time. And then you've had announcements. I think Toyota had a big announcement a couple years ago that they made a big breakthrough in solid state. I'll believe it when I see it. And the reason is there's a lot of difficulty in making the membrane, basically manufacturing the solid state battery. Because instead of having a flexible polymer membrane, now you have a more rigid ceramic membrane that you can't manufacture it the same way.
So when people are talking about a solid state battery, that's not like what you consider a solid state battery as a scientist. They're just talking about the separator not being like polymer, I guess. It would be what you call ceramic.
Yeah, generally that's how it's used, yeah.
So it's like a solid membrane.
Yeah.
Yeah. Mm-hmm. Okay. And then these polymer membranes, is it sort of like plastic with holes in it? Is that kind of what it is on the microscopic level?
Microscopic holes, yeah.
And then I remember reading somewhere too that one of the protective mechanisms for some of these batteries is when they get hot enough, it seals up those holes. It kind of melts the polymer and it seals up the holes.
Yeah. There have been definitely work done on that. And I think that is definitely possible. Yeah.
Mm-hmm. Okay. And then with one of these ceramic membranes, what happens when that one gets really hot? I guess it doesn't seal up the holes, but there's probably other reasons why it's safer, I would imagine.
Yeah.
It's not a piece of plastic.
Right. It's stronger and more rigid, and it's stable under most conditions. But, the challenge is you have to make sure that you don't have what's called dendrites that go through the ceramic. And so lithium kind of forming these metallic dendrites that can then short circuit the two sides.
And so dendrite, is that sort of like a Latin word for branches or something like that?
I think so.
Yeah. So I know that brain cells, they call those dendrites. And I've seen it too when studying batteries and things like that. And the dendrites look kind of like brain cells. And you don't want one going from positive to negative, from cathode to anode, and causing a short circuit, which would release all the energy at once, which is definitely what we don't want to have happen. And then also from what I've read too, is that's why we don't have rechargeable lithium metal batteries. So instead of having, graphite, you just have like solid lithium. Is that what that is?
That's right. Yeah.
And so the non-rechargeable lithium batteries, they have that. But when you charge them and discharge them a bunch of times, it could cause a short circuit. I remember though, I'm on this award committee for the Intersolar, the Smarter E, outstanding projects. And one time we did have somebody that was up for an award that was doing lithium metal batteries. but it was like in a third world country in an outdoor venue. And I think it was ones that weren't cycled up and down a lot. So perhaps they could harness the danger, like if something happened, they had it in a safe place where nobody would get hurt, or they didn't have as many rules to go by.
Yeah, I mean, people have made, certainly have made lithium metal batteries, but it hasn't been widely commercialized because of that problem.
And then I think they could hold a lot more energy per weight too, right?
Right. So, one of my friends and mentors from Stanford, Richard Wayne, started a company called Cuberg to make lithium metal batteries for airplanes, because you really have to get the energy density much higher than conventional batteries in order to think about flight with batteries. And even then, it was for kind of short haul.
Don't say short when you talk about batteries. Short.
Yeah, that's true.
And then I guess like with an airplane, you would worry about a short, and thermal runaway and all that stuff. But you could also drop the battery, I guess. Hopefully not over anybody's house.
Yeah, it's true. There's a lot to be figured out for that. Yeah.
Yeah, I remember taking some flying lessons, and that's like a big problem that you look out for is like an engine fire while you're way high in the sky. And how do you get down? How do you, aim the airplane in a certain angle where it might put the fire out? And then, you see like the big airplanes, if they're going to come in for a landing when they planned on going on a super long trip. I think I just saw something like that recently where they dump their fuel over the ocean or something like that, which, the fish love it. They get all that extra energy from that jet fuel.
Wow, I didn't hear about that. Yeah.
No, I guess it is real common to drop fuel. And I was kidding, note the fish do not love it. Yeah. But it is, not a good thing, dropping that kerosene down there. But yeah, so we were talking about lithium metal batteries, and they can be much lighter. What do you think might even happen in the future? Like, where are we going to be as far as energy per weight? What do you think we're going to see? Are we going to see, like, from your average battery that people are using right now, is it going to get twice as much energy per weight in 10 years and 4 times in 20? Or are there a lot of limitations there? Is there any way possible in 1,000 years that will meet the energy per weight of gasoline? And also with gasoline too, we have to take into consideration that most of that energy when somebody's driving with gasoline turns into heat. So that's exhaust pipes. There's a lot more heat coming out of your exhaust pipe than there is power pushing you forward.
Yeah, I would say, in my view, lithium-ion batteries are pretty amazing and are pretty efficient in their weight usage in terms of their chemical reaction. And, we've talked about different ways to improve them, like going to the lithium metal, going to a conversion cathode on the positive side. I don't see any of them as, very near term, but certainly if we think over a century, I certainly think that we will find ways to make more gravimetrically energy dense and volumetrically energy dense batteries. I think I would just personally say, I think we've really come to a very kind of exquisite engineering of lithium-ion batteries now, and it's going to, we can have some incremental gains, but we're not going to see, I think there's a lot of challenges to really big gains here.
Like I know with PV, there's a limitation. Like you asked a lot of, these PV researchers and all that kind of stuff. And it's somewhere like, 50% would be like the most you could ever get, and it might cost you $1 million for a watt or something crazy like that. And with batteries, I don't think you have those same kind of limitations.
So I think in battery, there are certainly hard limitations in terms of how much energy the reaction stores that, lithium-ion batteries are now above 50% of that theoretical. But if you look at how to design a battery to eke out more and more of it, it starts to get really difficult. And you have to then change the reactions. And if you change the reactions, then you have to solve all hosts of new challenges. So, I think something that maybe people don't appreciate as much from the outside and seeing kind of headlines about battery advances is that there's a lot of balancing that you have to do when you design a certain battery system. So you want to maximize the energy density, but you also want it to be stable enough and last a certain amount of time. You also want it to be safe. You also want to get that round trip efficiency up and get a good power density. And then you want the cost to be, reasonable. And usually if you see a big headline about advance in battery and some metric, usually that's not, they haven't taken one of the other metrics at least into account, and it's not something that's not as practical. So I think that's the big challenge in batteries, is how do you get something that advances all of the metrics you want without taking a big step back in one or two of them.
Yeah, and I guess some of the metrics would be like how many cycles,
Yep.
efficiency, and then, energy per volume and energy per weight. Those would be, I guess, some big ones. And I think too, with cars, it's good enough. I mean, my car is 10 years old this year, and it's like, I'm not a long haul trucker. It works fine for me. It's like, I never have to worry about, stopping to charge. I mean, I guess if I was an Uber driver or something like that, it would be an issue, but it's not a problem. Every morning it's as charged as I want it to be. But then you were saying other things like airplanes and all that kind of stuff. And I guess, the other big one too is price. Can't forget about that metric.
Exactly.
But do you think, we're going to make improvements, and you might say it's going to be, I guess it would depend on what metric you're talking about, but let's just say that if we kept all the other metrics kind of in check, say they didn't get worse. So round trip efficiency over 90% is kind of common. And then we have, the price, it's nice to get less expensive, and it will as manufacturing goes up. But I think a big one that people would really like would be how much per weight. And it seems to me too that per weight and per volume kind of go with each other to a certain degree.
Mm-hmm. Yeah.
So it's almost, you could just put those almost in one category, but you can't, but you sort of can. But to have a cost-effective battery that's over 90% efficient, are we going to maybe double our energy per weight and volume in the next 20 years, you think?
Let's see, 20 years is a long time,
Especially with you working on it.
Yeah. Yeah. We got lots of smart people working on batteries. I think it's a stretch. Personally, I would put it at less than 50% odds if I was going to make a prediction.
Okay.
It's in the realm of possibility, right?
So it's in the realm of possibility, and give it another 10 years and we're there, or something like that, probably. Yeah, okay. So that's really positive. And I guess it just depends on how many resources we throw at it. I know with solar, you always see all these articles new technology changes everything, and still it doesn't. It's we still have the same silicon-based rectangular aluminum frame modules that we had in 1954. And with batteries, it just seems to me too that there's a lot more chemicals and different things that you could do. It seems, I don't know, it seems different than solar to me for some reason like that. And then when, you're using a different element a little bit, it's lithium versus sodium, they're pretty closely related. They're right on top of each other on the periodic table. And so I guess what it would be 1 out of 8. What would you say, the orbits of the electrons? It's 1 out of 8. Is that what it is over there in that left side of the table? Mm-hmm. So to fill up the cell, it takes 8, and you've got 1 out of 8 there. And for some reason, that's really good for making batteries. And so do you think there'll be anything where they do something crazy, mix up sodium and lithium, or is that just ridiculous?
Gosh, I've thought of, me and my fellow Chew Group members at Stanford have thought of so many crazy battery ideas over the years. Yeah, you could certainly mix lithium and sodium. What's nice about, I really fixated on sodium because, I was looking at that column of the periodic table where you have the alkali metals, and they only have to lose one electron, and then they're a pretty stable ion. And that's something that, lithium ions, sodium ions, they're relatively compact. They can transfer pretty easily across from one side to the other. I think that's really important. You can think about other types of ions that can hold more charge. So you think of a magnesium battery where magnesium loses 2, it's the 1 over. So now it loses 2 electrons, it's an Mg2+, and each magnesium ion carries 2 charges across the membrane. Or you can think of a aluminum ion, where aluminum is now the next one over, and that's carrying 3 electrons, aluminum 3 plus. So that's a lot of charge for one ion, and that can make it really energy dense. And actually, you have a lot of groups now looking at aluminum metal as a charge carrier now for very high energy density. It's harder to recharge, but as a primary battery, primary way to transfer energy, that's, it's super energy dense. But then, the challenge is, that those 2 plus or 3 plus ions, now they're more reactive, they're more polarized, so it's harder to move them from one side to the other.
Yeah, my car has aluminum in it. So it's an NCA, lithium, nickel, cobalt, aluminum oxide.
Okay. Yep. Mm-hmm.
So is that kind of what you're talking about?
No, in that case, the NCA, the nickel, cobalt, aluminum, those are part of the lattice. We were talking about intercalation batteries.
Mm-hmm.
So the aluminum is just one of the metals in that lattice. But I'm actually talking about aluminum being like an aluminum ion battery, not lithium ion. Like the aluminum is the thing that's going across. That could be a way to get to higher energy densities.
Is anybody doing that?
Yeah. So there's groups looking at basically using aluminum as a carrier of energy because it's such an energy dense carrier, but then it's harder to recharge. I also want to kind of make a bigger point. I think it's really exciting, all of the work that's being done in the battery world, but, we are still using lead acid batteries. That was invented over, in the 1800s, over 100 years ago.
I've heard even 250 BC or something like that.
Yeah, if we talk about some chemistries going back that far.
Maybe it was a different one. Yeah, like something in Baghdad, the Baghdad battery. I don't remember what that was. Maybe that wasn't lead, but...
Yeah, that was a different one. But then we still use that. We still use alkaline batteries. We still, lithium-ion batteries in their current form, they're over 30 years old. And, what we're working on at Inlyte is a sodium metal battery, but, it goes back, you can trace its history back to the 80s, but actually even before that to the beta alumina batteries that were made in the 60s. So, I think it is true that there's a lot of different reactions that you can theoretically use to store energy, but when you apply, you have to get something that works reliably and stably under all sorts of conditions. You have to, when you have chemistry happening, a lot can happen in a chemical environment. And so this is why I'm a little hesitant at saying, I think we'll get to a certain, better performance of battery, better energy density, because we've seen advancements, but we've certainly seen how long it takes on a historical timeline.
I think that you're just not telling me because you're developing it yourself and you're going to come out with it next week and you're not ready to release all these great ideas that you have.
Well, we have a lot going on. Yeah, we have a lot in the hopper that,
Okay, great. And so maybe you could explain a little bit about electrochemical potential.
Okay. Yeah, I think this is really cool. So you may know that an alkaline battery is about 1.5 volts.
Yeah.
So why did they make alkaline batteries 1.5 volts?
Because that's what those chemicals do.
Exactly.
Like lead acid, 2 volts, lithium, NMC, nickel, manganese, cobalt oxide, 3.6, LFP, 3.2. And you can tell me what your battery is, I guess, the nominal voltage.
Our reaction is 2.35 volts.
And then the solar cell is about 1/3 of a volt per cell nominal.
Yeah. So, we deal with 12 volt lead acid batteries because it's 6 2-volt cells stacked in series to get to that 12 volts.
No matter how big the cells are, you could have a cell that's the size of a swimming pool or the size of your little finger, and it's going to be the same voltage.
Yes, because the cell is composed of those 2 sides with the membrane in between. And so, those could be much bigger, but as long as you have those components, then you're going to get that voltage. And, that's just a fundamental property of the chemical reaction. And it's just directly related to the chemical energy that's released in the reaction. So,
and I guess it's also the same with like corrosion and rust. It's related. It's like a battery. Like you even mentioned rust earlier today.
Yeah. So you have, voltage is a measure of energy per charge. So it's joules per coulomb. And so if you combine the voltage of the battery with how much coulombs have crossed, so how many ions have crossed that membrane, is coulombs is a count of, of electrical charge.
I think it's like 6 quintillion. something like that, a coulomb. I think like a
1.6
coulomb,
times 10 to the minus
or in
19.
a second. Yeah, in a second. Coulomb second is an amp, right?
Yes, an amp is a coulomb per second. But anyway, I guess what I was getting at is the voltage is just a measure of basically how much energy each ion carries per charge of that ion. So a lithium ion is one charge, and so how much energy does that lithium ion carry when it's crossing over in the battery? That's what the voltage is measuring. So generally it's, you'll get to higher energy densities if you have higher voltages.
Great. Yeah. So, I mean, it's always good. And so,
but then usually that also means the battery may be more reactive because you have things that are at a more unstable potential, and then you have to figure out how to manage that. So
what would have a higher nominal voltage? Is there anything that goes above, like our lithium ion batteries we put in our cars, which is like 3.6, or some people define it as 3.7 volts? That would be like the lithium ion battery that has some cobalt in it, like the NMC, lithium nickel manganese cobalt oxide. So can we get up to 4 volts? Can we get up to a megavolt? Maybe inside a black hole.
Here is one way to think about it for the chemists in the audience, or people who at least love chemistry. So if you think about an ion that's carrying one charge, so the amount of energy it's carrying, it would be we would call it an electron volt. And 1 electron volt per atom is it's 96.5, but it's about 100 kilojoules per mole. And kilojoules per mole is how chemists often refer to the bond enthalpies, the strength of the covalent bonds in molecules. So for example, a carbon-carbon bond, in sugars and in all sorts of carbon-based systems, so that's about 350 kilojoules per mole. So if your battery was reversibly breaking that carbon-carbon bond and putting it back together with some ion crossing over, so it would have about 3.5 volts, very roughly. So another way we could ask the question is, what's the strongest chemical bond that we have that we could theoretically put into a battery and then, be reversibly breaking that? And I mean, I think the strongest chemical bond I've written down here, and there's for sure probably stronger ones, but you have in nitrogen molecules, so nitrogen-nitrogen bonds, which are triple bonds, and they're very hard to break. So that has a bond enthalpy of 900 kilojoules per mole. And if you could theoretically make a battery that went, N2 and was able to break that triple bond and then put it back together, that would be a 9-volt cell.
Wow. Is that possible, though? Has anybody done anything like that?
Yeah, I don't think so.
Maybe on a different planet, something like that? Maybe someday where humans will be smart enough. Maybe you'll figure it out next week, because we challenged you here.
There is so much that humans still have to figure out. I think that's the beauty of science. And, the more we have people being curious and trying to figure that out, the better.
Okay, great. Well, thanks for all of your super smart intercalations. I'm just using that word just to sound smart. And we were also going to talk a little bit about some non-science stuff, such as celebrity, like business builder celebrity Bill Gates, saying that he knows stuff about things that he didn't study in school. So what's been happening with that?
Yeah, I mentioned that because I do have some strong views on it. Bill Gates came out a couple of weeks ago with a blog post where it was titled 3 Tough Truths About Climate. But the gist of it is that, and it's a very well thought out post, although I would disagree with a lot of the reasoning there. But, he made a lot of nuanced arguments saying climate change is still a serious issue that deserves serious attention. He just said basically, he doesn't think right now it is a top priority of, for example, the climate community that's meeting now at the COP conference in Brazil. In his view, we're not going to have a doomsday scenario with climate, and we should be focusing on the things that you can measurably improve human welfare, and we should figure out all of those things and make sure we do them, prioritize those before kind of, and not just focus on climate change. So that's how I understand his view. And I think, to your point about, why should we listen to him? I think that's exactly the point. And I think it's gotten a lot of attention from both sides of this debate. Climate change has gotten really polarized. unfortunately. And basically, you have one side saying, well, look, now Bill Gates says we don't have to worry about climate. So it's not, he was fooling us all along with he wrote a book just a few years ago about how to prevent a climate disaster. So people are holding up his conclusions as, oh, my side's right. And I think that is exactly what we shouldn't be doing. We shouldn't be trying to, govern humanity and what humanity's priorities are based on what a certain billionaire thinks, or, even just a certain group of elite. I would even argue like we should not have this group of scientists that determine everything about how we're going to govern society, even if they happen to be right about climate change. In my view, this is the route to a closed society, Plato's Republic, in essence, an authoritarian state. And what I value is freedom and democracy. And I think that's why climate change is so challenging, right? This whole debate just shows why it's so hard for us to figure out, how to prevent this, because everyone can take their own opinions on this. Every country can act in its own self-interest, and they should. But you have this huge tragedy of the commons where if we don't have collective action, we're just going to keep increasing the warming on the earth. And it's something that we actually will not be able to see what the effects are directly until many decades from now, potentially. But our actions today influence that. So, I think people, in my view, yes, I disagree with Bill Gates about his conclusion, but I think it's actually the reasoning that gets me more about it.
Yeah, and he stole the mouse from Steve Jobs, man.
Yeah.
There was software and all that stuff,
Yeah, right. But I admire him for his philanthropic efforts. It's been really amazing what he's done with the wealth he's accumulated and how he's tried to put that to good use. And if he decides his priority for his philanthropy is not climate, that's totally fine with me. Mm-hmm. I think everyone should make their own decision there. But what doesn't make sense to me is saying to the world, this is how everyone should think, because that doesn't allow for freedom and democracy.
Well, what's the real solution for climate? It's you and I and all of our listeners here. That's us. We're going to make renewable energy so prevalent and so cost effective that using burning stuff is going to be stupid.
Exactly.
That's a solution. And then that's a solution too that everyone's going to get on board with. I mean, I guess there'll be a couple people like, let's just burn something because, we want to burn it, those coal rollers and stuff like that. But that's the solution. And it's coming to be,
Exactly. And, if I could just add one more thing to that, I would say also a view that Bill Gates expressed that I disagree with is this sense that, all that matters is what is the green premium about for the renewable solution, the green solution. If we drive that to zero, so it's now cost effective to put in the green solution, then the problem is solved. Like that's how he puts it. And his view, we're on a good trajectory for that. And then the problem is going to be solved. In my view, and Jigar Shah kind of shares this view, he has a much, much hotter take than me, but it's not just about that. It's actually, it has to make sense for everyone involved. It has to be able to be deployed. It has to be able to be financed. It has to, people have to accept it as a solution. And part of that is countries deciding what's in their best national interest. So, I think we have this huge backlash in the US now against what's happened economically over the last 50 years, where we've had a hollowing out of America's manufacturing core that's gone to China. And, people, even though they make low cost things that we buy, that's not working for our society. And, I think we have to think about the solution to climate change. It has to work for each country and make sure it's in that country's national interest, not just their economic, just looking at the pure economics. And so for me, what really drives me is, our battery, we can make this in the US, we can source it in the US. We are not dependent on China for anything, no materials, no equipment. You can't say that about lithium-ion batteries or sodium-ion batteries. Even if we build factories here, we're going to be dependent on Chinese supply chains for a long time. And, there's this backlash now against that. So, yeah, I think finding the solutions, and not just in terms of technologies, dollar and cents, but in how you can manufacture it, how you can produce it, deploy it. So everyone has this interest to do it. I think once we find all of those, then we'll really have solved the problem.
Yeah, we're going to make it. So if you were in Texas sitting on a brand new oil field, it would be smarter to just put up some solar and wind turbines on that oil field than it would be to pump that stuff out of the ground. And I mean, economically smarter.
Yes, exactly.
That's the trajectory that we're headed towards, and that's what we're going to do. The one scary thing, though, still is like, even if we stopped burning stuff today, the Earth's still going to heat up for a while. And they talk about 2 degrees Celsius lately, it seems like. And they oftentimes don't even say Celsius. And you got to convert it. 2 degrees Celsius is 3.6 degrees Fahrenheit. And that's probably where we're at. I don't know if we don't do anything, because that stuff stays up there in the air for a lot longer of a period of time. And we've got a lot of things that are melting and, some scary stuff going on.
Yeah. The current projections with the policies that countries have kind of pledged, but we're still not sure if they're going to follow through. But with that, it's about 2.5 degrees under my understanding. And
man, it goes up every day. Huh?
It could, if things go differently, it could definitely be higher than that. And
so 2.5 times 1.8 is 4.5 degrees Fahrenheit.
Right. And do you know the difference in global temperature between today and the last ice age?
You're going to tell me. I know that you're going to tell me. I know that you know.
It's close to 10 Fahrenheit, so 5 degrees Celsius-ish. So, we're talking about having changed the Earth in a hotter direction, but halfway to the amount that would have gotten us to an ice age if we had gotten it in a colder direction. And we don't know what the effects are of 2 degrees, 2.5 degrees, 3 degrees. And so, that's where Bill Gates can come out with an opinion and say, I don't think it'll be that bad. I think, Iowa will just be a little warmer, kind of like Texas, is something he kind of wrote in that note. And, we don't actually know. We don't know all of I can point to actually many other really serious effects that we are pretty sure are going to happen that he hasn't talked about, but we don't actually know. And that's what makes this challenge so hard, is we're kind of hurtling towards this unknown future at a ever increasing rate of our emissions.
Yeah, then you have like fresh water, and you also have people wanting to migrate north to where it's not so unbearably hot and dry. And those are things that perhaps we are seeing wars happen over already. But the number one thing that we've had wars for is energy. Even going back to Genghis Khan with, grass for your horses to eat. It's all about energy, Food is energy, oil, and of course, electricity. What we're in the business of dealing with.
Energy is essential. Yeah.
Yeah. Well, yeah. If you want to live.
Yeah.
Great. Okay. All right. Well, yeah, I really enjoy talking to you, and I think we should, have some more talks.
Yes. Let's do it.
Yeah. Yeah. Okay. All right. So
thank you, Sean.
Yeah. Thanks, Antonio Baclig. And how about just letting people know where they can find you and your company, where they can send millions of dollars, help you with your battery factory?
Yeah, any investors, we are always raising more money, but, customers as well. If you're interested, particularly, we're focused on providing solutions for behind the meter or front of the meter utility scale projects, utilities, developers, data centers, commercial industrial customers. We have a really, really good solution, really low cost and very safe technology. So the name of the company is Inlyte Energy. That's INLYTE. You can find us at inlyteenergy.com. I'm also on LinkedIn, and give us a shout. All right. And we will put all that information in the show notes. So thank you so much, Antonio Baclig. And thanks for listening to Sean White's Solar and Energy Storage Podcast, where you can learn about all kinds of cool stuff about solar, about storage. And if you want to even learn more, you could go get yourself NABCEP certified, or you could just take some of my free classes. Go to SolarSEAN.com. That's SolarSEAN.com.
and you can get yourself up to speed and understand Antonio Baclig a little bit better the next time we have him on the podcast. So thanks a lot, Antonio.
Thanks, John.
Woo!